Hey, Math 20-2. Today we're going to look at some deductive reasoning. Before we do that, let's review inductive reasoning. Recall that inductive reasoning is a type of reasoning in which we arrive at a conjecture based on experience, observations, or patterns. All right. Inductive reasoning, however, does not guarantee that a conjecture is true in all cases, no matter how many examples we have to support this conjecture. Just because we can't find a counterexample doesn't mean that one does not exist. So inductive reasoning can never be used to prove a conjecture. In order to do that, we have to figure out another method of reasoning, and we're going to use that other method to make a proof. We'll look at that method today. So logical or deductive reasoning. So using logical reasoning. Susie dropped off her film. That quick 1 hour photo. Quick 1 hour photo advertises that your film will be developed within 1 hour. Well, there's no charge. Susie dropped her film off at 10 a.m. and it wasn't developed until 11:15 a.m. What can Susie deduce from this information? Well, she should deduce that her film should be developed for free. It took longer than the hour, so there should be no charge. Deductive reasoning, or logical reasoning, is the logical process of using true statements to arrive at a conclusion. In the scenario above, Susie used deductive reasoning to conclude that her film should be developed for free. Example 1 then, write a conclusion for each of the following statements based on deductive reasoning. Every whole number is an integer. 6 is a whole number. Based on these two statements, 6 should then be called an integer. Part B. Water freezes below 0 degrees Celsius. The temperature is minus 15 degrees Celsius. What should we say? We should say that, well, the water should be frozen right now if it's minus 15 degrees Celsius. Note, a theorem is a statement which can be proved using logical or deductive reasoning. So once we've used some deductive or logical reasoning and proven a statement, we call it a theorem. So lesson 1, class example 4, we used inductive reasoning to write a conjecture about the sum of 3 consecutive integers being divisible by 3. Use deductive reasoning to prove the following conjecture. The sum of any 3 consecutive integers is a multiple of 3. So step 1, if I want to use deductive reasoning, I want to introduce some variables. So I'm going to let the variable n equal the first integer. Therefore, what variables would the second and third integers be? So if they're consecutive integers, if n is the first one, the second integer should be n plus 1, one more than the first. You could say n minus 1, that'd be fine. And the third integer should be one more than the second one, so n plus 2. So now if I write down what this statement says, the sum of any 3 consecutive integers, so let's add up our 3 consecutive integers. N, add n plus 1, add n plus 2. And let's see what that gives us. N plus n plus n is 3n. 1 plus 2 is 3. 3n plus 3, that should be a multiple of 3. Doesn't matter what value of n we plug in there, all right? So we could say that 3n plus 3 is always a multiple of 3. How do we know that? Well, I could maybe take this one step further over here, and I could maybe factor out the 3, and that leaves me with n plus 1. So it doesn't matter what number I put in for n. If I add 1 to it, and then if I multiply it by 3, that makes it a multiple of 3 by definition. All right, so 3n plus 3 is always a multiple of 3. Let's look at example 3. Complete the chart and make a conjecture using inductive reasoning. All right. Inductive by example, not deductive. So choose a number less than 10. I can pick any number I want. Less than 10, I'm going to pick 3. Add 7 to 3. Multiply that by 2. 10 times 2. Subtract the original number. The original was 3, so 20 minus 3 is 17. Subtract 2 from this. 17 less 2 is 15. And then subtract the original number again. 15 minus 3 is 12. All right. You guys do a second and third test case with a number less than 10. Away you go, and then you pause this and do that, and you can start it up again and see what we all get. My numbers might be the same, might be different. Away you go. So you go through your 2 other test cases and look at the bottom row, and it seems to us that no matter what number we choose or start with, no matter the number we start with, the final answer is 12. Now, prove this conjecture using deductive reasoning. So we used inductive reasoning with 3 cases. You guys might have different ones, so maybe we've got 5 or 6 different examples there. But we can't do it for every possible number less than 10. There's an infinite number of numbers less than 10. So let's prove our conjecture using deductive reasoning. Let x represent the original number chosen. So x will be a number less than 10. So now let's add 7 to x. X plus 7. And then multiply that by 2. So 2 times x plus 7, or we could say 2x plus 14. And now subtract the original number. So 2x plus 14, and we're going to subtract the original number of x from that. That gives us 1x plus 14. Now subtract 2. So we've got x plus 14, take away 2, gives us x plus 12. And now we subtract the original number. Well, x plus 12, we take x away from that. We always end up with 12. It doesn't matter what that number x is. All right? So we've proved that whatever the original number we start with is chosen, the final answer will always be 12. Part D says, does the original number have to be less than 10? Well, up in our original general case here, when I chose x, I didn't really say that x has to be less than 10. I just picked x as any number. So we can say that, no, x can be any number. No, x represents any number. Doesn't matter what that number is. You'll still end up with 12 at the end of that little procedure. Note at the top of the next page. In this lesson, we'll be considering statements involving odd numbers and even numbers. Note that when we use the notation 2n, where n is an element of the natural numbers for even numbers, you pick any natural number, n, and you multiply it by 2, you're going to get an even number. You pick any natural number, n, and multiply it by 2, you get an even number, and then if you subtract 1 from an even number, you're going to get an odd number. Or if you add 1 to that even number, you're going to get an odd number. So these are our variable statements for odd and even numbers we're going to use in deductive reasoning. So explain why 2n can be used to denote every even number. Well, every even number is divisible by 2. And 2 times n makes every number divisible by 2. n minus 1, why is that denoted for every odd number? Well, we just said 2n makes every number an even number. If we subtract 1, subtract 1 from an even number, it becomes odd. All right. Example 5. Consider the following statements. When two odd numbers are added, their sums are always even. Use inductive reasoning. We'll try 3 examples to suggest the statement's true. So we can pick any two odd numbers, add them, we should get a sum that's even. 1 plus 11, those are two odd numbers. How about 13 plus 27? Those are two odd numbers. I add them, I get an even number. What about 111 plus 13? That's 124. So if I add any two odd numbers, it seems that their sum is an even number. But I've only done 3 cases. I can't do every case to make this true, so I'm going to use deductive reasoning to complete the proof. So this got me started. I have an idea of what's happening. Let's use deductive reasoning to prove that this is a true statement. So we're going to let 2n minus 1 be one odd number and 2m minus 1 be the other odd number. So if I add those together, 2n minus 1, add that to 2m minus 1, what do we come up with? Well, you get 2n's plus 2m's. Negative 1 plus negative 1 is a minus 2. Well, if you remember how to factor this statement, these 3 terms have a common factor of 2. So if I factor out a 2, I get n plus m minus 1. Every term here divisible by 2, n plus m minus 1. Now it doesn't matter what n is, and it doesn't matter what m is if they're both natural numbers. Whatever number I get in the brackets, whether it be an even number or an odd number, once I multiply it by 2, that's going to make it an even number. All right? So this signifies a multiple of 2. And every even number is a multiple of 2. Or is divisible by 2. Therefore, it's always an even number. Note, we will explore deductive reasoning further with 2-column proofs in the next unit, reasoning with angles and triangles. We're not going to do that in this unit. All right? So you guys have your self-assessment. There's some questions to try.